Hi, I am Barsegh from Pixart AI research team. In this video, I'll present our WACB 2024 paper, Continuous Adaptation for Interactive Segmentation Using Teacher-Student Architecture. Interactive segmentation is the task of extracting masks for user-specified objects or regions of interest. User annotations can be of the form of scribbles, clicks, bounding boxes, polygons, etc. Applications of interactive segmentation vary from image editing to annotation of large datasets for image segmentation, for self-driving cars, aerial or medical imaging. Nonetheless, the performance of current state-of-the-art methods deteriorates on datasets from unseen domains. To address this issue, some methods apply test-time adaptation to update the model based on user annotations which provide strong hints about the ground truth. These methods have shown promising results on adapting to a single dataset from an unseen domain. However, in most practical scenarios of large-scale annotation, the target domain is not stationary, meaning that datasets from different domains might become available for annotation. In such cases, catastrophic forgetting becomes prominent in adaptation methods for interactive segmentation. To that end, we propose a method to update the model in a way that it accumulates knowledge from new datasets without forgetting the existing one. Our contributions in this work are the following. We propose a new method for continuous adaptation for interactive segmentation that alleviates catastrophic forgetting and can use any pre-trained off-the-shelf interactive segmentation model. As part of the proposed method, teacher and student models are updated based on user-provided clicks and previous predictions to adapt to new domains. Through various adaptation scenarios, we demonstrate the effectiveness of the proposed method in adapting to new domain datasets, while diminishing catastrophic forgetting for training domain datasets. By our design, both the teacher and the student models have the same architecture and the same initial knowledge. During adaptation, they constantly exchange their knowledge. Particularly, the teacher model shares its knowledge with the student before the adaptation on each dataset. Then, the student model quickly gets adapted to the new dataset and exchanges the new knowledge with the teacher. Going into more details, at the beginning of adaptation, both teacher and student models are initialized as the pre-trained interactive segmentation model. To adapt to a single image from a new domain dataset, after each click we perform a single gradient descent step to update student model parameters. The loss consists of two components: sparse cross-entropy between the current prediction and the user clicks, and a regularization term to penalize large deviations from the initial weights. After there are no more corrections from the user and the interactive process has ended for the current image, we use a single gradient descent step to update student model parameters. This time, another regularization term is included in the above described loss, a binary cross-entropy between the initial and final predictions. After obtaining a final prediction for the current image, we update the teacher model as well. To achieve the initial objective for the teacher model and accumulate new knowledge without forgetting past one, the teacher model is updated by the exponential moving average using student model parameters. This way, the adaptation is done iteratively for both student and teacher models, updating student model parameters after each user click and updating teacher model parameters once for each image. To adapt on the next dataset, the teacher model stays as is, and the student is reinitialized with current teacher model parameters, and the above described adaptation process is used again. With such design, frequent updates with student achieve improved performance on the current domain, while updating the teacher via exponential moving averages leads to a balanced knowledge accumulation from past and current domains, deteriorating forgetting. We demonstrate that our method helps to achieve better performance on new domain datasets both quantitatively and qualitatively. Furthermore, we illustrate the effects of catastrophic forgetting doing continual adaptation first on one or two new domain datasets and then each of pre-training domain benchmark datasets. Using a baseline method for continuous adaptation on the specified sequence yields significant forgetting for each of the benchmark datasets. Meanwhile, applying the proposed teacher-student architecture eliminates the effects of forgetting. To verify that our approach can be applied in a plug-and-play manner, we utilize recent state-of-the-art interactive segmentation models focal click and read. Qualitative results also show that our method diminishes catastrophic forgetting. We also demonstrate that our method yields improvements over the state-of-the-art interactive segmentation models on training domain datasets. In conclusion, we have presented a novel plug-and-play method for interactive segmentation that leverages a teacher-student architecture for continuous adaptation for any pre-trained interactive segmentation model. Our approach addresses the issue of catastrophic forgetting that arises when adaptation is done on several datasets from different domains sequentially. The proposed update rules for teacher and student models enable not only to improve performance on different domain datasets by a large margin, but also to achieve better results on benchmark datasets from the training domain. We believe that our proposed method provides a promising direction for future research in the field of continuous adaptation for interactive segmentation and can be applied to a wide range of applications such as digital, aerial, or medical imaging. Thank you very much for your attention.